Hi students, welcome to Year 10 Science and the Motion and Energy topic, and in this one we're just going to go back and review some graphs. This was a skill that we looked at a little bit earlier in this topic, and it's one that I thought it's probably worth just having a short video up here just to give you an idea of the sorts of things that we're doing with our graphing of motion. So there's two different types of graphs that we're going to ask you to be able to interpret, and they are distance versus time graphs and speed or velocity versus time graphs. The most important things about these graphs is to determine from the axis which of the variables is on the y-axis. Usually it will be time on the x-axis. And then some of the things that are very important and common to both of these two graphs mean very different things. So a horizontal line on a distance time graph is an indication that the object is stationary, and that is that its velocity is 0. A horizontal line on a speed time graph just means there is no acceleration, and that is equivalent to saying that the speed is constant speed. Now, only if that horizontal line happens to be on the y-axis and therefore with on the x-axis and therefore with a y value of 0 would we say that the object is stationary. This is just an indication of constant speed. Likewise, if our graph is a straight line between each of these, I might just try and straighten that one up a little bit. It's not much better, but a little bit better. Then again, it depends what we're looking at. If this is a distance time, then this is covering a certain distance in a certain time, so it's going at a constant speed. As long as we're talking about distance versus time. But of course, if we're talking about velocity versus time, then a line like this is going to be an indication of constant acceleration. That is increasing speed. So let's have a look then at two important differences between these, and hopefully we'll be able to identify exactly what's going on here. So you can see a couple of distinct regions on this graph. Because this is a distance time graph, then anything that is a horizontal region is going to be a stationary position, that is velocity or speed is equal to 0 meters per second. The graphs can also indicate some positions even though they are distance versus time. So if it starts at 0 and then it ends at 0, this is equivalent to the object returning to the start. The gradient, or how steep the slope of the line is, tells you something about the speed of the object. So a line that is very, very shallow or very slowly sloping is going to be a slow speed, slow increase in distance over time, whereas the green one here is obviously rising very quickly. It has a steep slope, and therefore it will be a very much higher velocity. Just as an interest one here, of course, if acceleration is occurring, then the speed is constantly changing, and we can actually work that out by drawing tangents to the curve at any point. But this is something that you'll do a little bit more of in your physics course in the senior years. So contrast that with a velocity time graph, and two important things become clear. Firstly, when we look at a horizontal section of the graph, we actually have a value. That's a constant speed. So the acceleration here is 0 meters per second squared, but the speed is constant. I've included one here which shows you areas of acceleration. So this is where the speed is increasing, and also areas of deceleration, okay, which is where the speed is decreasing. In fact, positionally, this object actually goes through that starting point. So it could actually be behind effectively where it was to begin with. Now, this is not a position, this is a velocity, so it is going to be interesting in the way that we interpret these things. But one other thing that's important that you can get from a velocity time graph is what we call the area under the graph. So this area under the graph here would be equivalent to the distance or displacement, total displacement throughout that journey. Now, if you know how to calculate the area of a trapezium, you can do that, or you can split this up into two right-angled triangles and a rectangle and work it out that way. Likewise, this area here would also be equivalent to the displacement that the object, or the amount of distance that was covered in that period of time between the 30th and the 55th minute. It's important to make sure that you check the axes first, because the axes are going to tell you how you're going to interpret these velocity time graphs, and we will have a look at a few more examples in class. Thanks for watching.